Study the flowchart and answer the questions that follows. I have two processes here, as you can see from the diagram. On my left, I have a process with chambers, and on my right, I have a process with chambers. I'll let you know in a short while what these are. So, before you ask any question on a flowchart, a student is required first to understand what is happening in the flowchart with the help of these arrows that are indicated here. So, on my left, where we have hydrogen and nitrogen being let into a chamber, that process is known as a haber process. Haber process. Haber process is an industrial manufacture of ammonia gas. And on my right, we have another process which is known as the contact process. Contact process. This is an industrial process where we manufacture dilute sulfuric acid. So the question revolves between the two processes. I will begin with the contact process. The contact process. So with this, as you can see, we have air being let into this chamber, and at the same time we have sulfur 4 oxide gas being let also in the same chamber. So they are reacting sulfur 4 oxide with air. So why have I written oxygen? Is because oxygen is the most reactive part of air, the most active part of air. So I have taken oxygen. So we are reacting oxygen in this chamber in the presence of a catalyst known as vanadium 5 oxide. This is a catalyst. It's a catalyst which they have named as catalyst D. So that is vanadium. Vanadium 5 oxide. So in the presence of this catalyst, these two will react to give out sulfur 6 oxide gas. Sulfur 6 oxide gas. Let's balance the equation. Sulfur is 1, 1. Oxygen is 2 on this side, and this is 3. Let's make 3 even by multiplying by 2. So sulfur in turn becomes 2, and this will also be 2. Oxygen, this is 4 plus 2, 6. 3 times 2, 6. So the equation is balanced. So in other words, what is being formed in this chamber after reaction is sulfur 6 oxide gas. So what is coming into chamber F? It is, we are now aware that this is sulfur 6. So sulfur 6 is being reacted. Sulfur 6 is entering into this chamber, and at the same time they are also adding what? Conc sulfuric acid. So this is plus conc sulfuric acid. Conc sulfuric acid, the state symbol is L. If you write aqueous, then you are simply saying that it's dilute. So this is conc HC sulfuric acid, so the state is L. When conc sulfuric acid is reacted with this gas, what we end up forming? We end up forming something known as oleum. It's a liquid. It's liquid in state. So we end up forming a liquid known as oleum. Oleum. So we are forming oleum here. S is 1. Plus 1, 2, 2. Hydrogen is 2, 2. Oxygen is 3 plus 4, 7, 7. So it's balanced. So what we know as per now is that what is entering G is what? Is oleum. Oleum. This is the oleum I'm talking about. Finally, in this process, the contact process, what are they adding to G? Enough water. Enough water. So we have H2S2O7, that is oleum, they are adding water. So we end up forming dilute sulfuric acid. Dilute sulfuric acid. I say dilute is aqueous in state, conc is liquid in state. In state. Let's balance. H2 plus 2, 4. So we put 2 here. And I think the equation is balanced. S2, S is 2 because of this. Oxygen is 7 plus 1, 8. 2 times 4 is 8. So what are we letting into vessel H? we are letting in dilute sulfuric acid. Let's come back to this side, the Haber process. Let's discuss the Haber process. The Haber process, then we conclude with the question. The Haber process. So in the Haber process, two things are being reacted, that is hydrogen gas is being reacted with nitrogen gas, so we end up forming ammonia gas. In the presence of a catalyst here, that catalyst is normally said to be finely divided ion catalyst. So that is our catalyst, as they have named it, catalyst C. So this is the C we are talking about at that pressure. So we have our gas there. So what is coming into E, we are aware that this is ammonia gas. So ammonia gas is being let into E, and finally it also gets into vessel H. So we still also have ammonia here, ammonia gas. So what are they saying? Ammonia is reacting with what? Sulfuric acid. Ammonia gas is reacting with dilute sulfuric acid is a gas. So we end up forming a fertilizer, which is this. The name of this fertilizer is ammonium sulfate. Now, ammonium ion is written that way. When it combines with the sulfate, we end up forming this compound times 2. So we end up forming NH4, 2, then the sulfate term times 1. So this is the fertilizer. That is the fertilizer, ammonium sulfate. Is it balanced? Let's see. N1, N2. So we put 2 here. H is 6. H is, okay, this is 2, 6 plus 2, 8. 4 times 2, 8. S is 1, 1. Oxygen is 4, so the equation is balanced. So we are aware that this fertilizer here is ammonium sulfate. Ammonium sulfate. So I think I've discussed the point well. What were the questions that I was supposed to answer? So very quickly I'll answer the questions because I have discussed the flowchart. We discuss the questions. Number 1, they wanted to know what is catalyst C, which I think I have given the name. Catalyst C is finely divided ion catalyst. Finely divided ion catalyst. Number 2, they wanted to know the sources of this hydrogen gas in this diagram. Where does this one come from? Hydrogen gas mainly it comes from natural gas. Natural gas in organic chemistry is known as methane gas. Methane gas is CH4. So we obtain nitrogen. We obtain hydrogen from there. Number 2, the other source for hydrogen gas is cracking of long chains of alkanes. Long chains of alkane. I'll just give an example. If we have a compound like decane, 10 molecules of that, and this is 22. When we cracking, we may end up forming 2 compounds of propene, 2 compounds of ethene, plus hydrogen gas. So this hydrogen comes from cracking this. We have cracked this. We ended up having propene, 2 compounds of propene, 2 compounds of ethene, and finally we have hydrogen gas. So the other source for hydrogen gas is cracking of long chains of alkanes. So I think I've answered the sources for hydrogen gas. But remember, mainly hydrogen is gotten from methane gas, natural gas. The other question was this, from the chart, or rather from the flow chart. What are the sources for this nitrogen gas? The sources for this nitrogen gas. The sources for nitrogen gas, nitrogen simply comes from fractional distillation of liquefied air. These are Form 1. Liquefaction of air was discussed in Form 1. But if someone has a concern or a question, you can raise it, then we'll discuss it later. But if you are at nitrogen, at Form 1 level, you are taught on how to separate nitrogen from argon and also from oxygen. So that is the source for nitrogen gas. The other question that was asked was chemical equation at vessel H. Vessel H. I had written the equation already. We had ammonia gas entering into that vessel, and what was also getting in was this sulfuric acid, which I said we get ammonium sulfate. I had written this equation. This is the balancing figure. This is gas, this is aqueous, dilute, and this is a fertilizer, which is solid. I think it's balanced. The other thing, the other question was equation at F. I had also written the same equation at F. So equation at F. So equation at F, what was getting in F was sulfur 6 oxide, and also they were adding conch, sulfuric acid. Conch, I said use letter L for state symbol. This is a gas. We ended up forming oleum, which is also liquid instead. That equation is balanced. Lastly, they asked, what are some of the industries? Some industries or farms that can be set up near this particular process. One of the industries that can be set up near this process, remember there are two processes, haber and contact process, are some industrial farms, fertilizer manufacturing farms. Because at the end of the day, when we collect our sulfuric acid and we also collect our ammonia, combining the two, we end up forming a fertilizer. So it will be very economical and useful to have an industry nearby the two, where we manufacture our fertilizer. Then the last kind of industry I would say is a power manufacturing industry. Power manufacturing industry. I'm talking about industries such as Kenya Power and the rest, those that produce power. This process requires high temperatures. So it will be very economical to have a farm that is nearby that supply it with the necessary or with the needed temperatures. So we will need such kind of farms nearby. Fertilizer manufacturing farms and also power manufacturing farms. I think I've answered the question. Thank you.